Hello, today we're going to talk about quantum operations, and this is inspired by the visual representation presented in Q is for Quantum by Terry Rudolph. So imagine that we drew operations this way. Let's say we have an operation named eat one cookie. I would start with a plate with 4 cookies on it, and if the operation eat one cookie is applied, then I have 3 cookies left. Okay? Likewise, I could start with 3 cookies and apply the eat one cookie operation, and I would be left with 2 cookies. Okay? So a few important points about this representation. One is that you can see operations progressing from left to right. That is merely the order of operation. It doesn't mean that this plate moved through a box. A cookie was eaten inside the box and then it emerged on the other side. This is just an abstract representation that tells you that you started with 4 cookies and then the eat one cookie operation was applied and then the result was 3 cookies. We could also have 2 operations in a row in sequence. So if we started with 4 cookies and then we ate 1 cookie twice, then we would end up with 2 cookies instead of 3. Okay? So once again, this doesn't mean that there were 2 separate eat one cookie boxes. It just means that the eat one cookie operation was applied twice. Okay? All right, so let's imagine an operation we call not. And in quantum, we have 2 values. So it could be apples and bananas, it could be happy and sad. And so a not operation toggles between these 2 values. So if we had a system where we had apples and bananas, if I started with a banana and put it through a not, I would get an apple. If I started with an apple, I would get a banana. And so we could use any 2 items and the not toggles between them. So in a quantum system, we're using 0 and 1, and we've put them inside this ket. We'll learn about the bracket notation later, but right now we just know that we have a 0 and 1. We will label the white ball 0 and the black ball 1. So in this representation, we have 2 choices, white and black balls. So the not operation toggles between them. So if I start with a white ball, then I end up with a black ball. If I start with a black ball, I end up with a white ball. All right, so I'm going to have a series of examples in this video that are challenges for you to figure out. And so each time you see one, feel free to pause the video, think about it, have a guess, you want to predict the answer, and then put the video back on and I'll go through the solution. So go ahead and pause the video now and try to figure out what it would be if we had multiple nots in a row in these cases. Okay, so let's go through the solutions. If you start with a white, apply it a not, that'll be black, and apply it again, it'll be white again. Likewise, if I start with a black, then we'll end up with a white after a single knot, and then a black after a second knot. So we've applied these knots twice, we get back to the original value. Okay? All right, so if I were to apply it 3 times, the first 2 get it back to the original value, and now I apply it again, and I'm left with a white ball. All right, so here's a second operation. It's called the swap operation. And in this case, each ball takes on the value of the opposite ball. So it's not moving the balls. Notice the dotted lines are to indicate that the top ball is still the top ball. It just changed color. Okay? So if we have a black on top and a white on the bottom starting out, then we'll have a white on top and black on the bottom starting at the end. Okay? Likewise, the white on the top and black on the bottom will end up with a black on the top and white on the bottom. If the 2 values coming in are the same, then a swap does nothing. They will remain the same. Okay. All right, so now let's try some multiple swaps as well as combining knots and swaps. So if, again, you can pause the video, think about it, predict what the outcomes are, and then we'll check our work. Okay, so if I start with a black ball on top and white ball on the bottom, after a single swap, the white will be on the top and the black will be on the bottom. And then the values will swap back again. So we end up with the same values we started with, just like the not operation. So these are their own inverse. If we apply it twice, we get what we started with. All right, let's look at the second one. So first I will apply the not gate to the bottom ball, which gives me a white ball on the bottom and black ball on the top, and then a swap. So they'll swap values, but not location. So now the top ball will become white and the bottom ball will become black. All right, so now our third operation is called a controlled NOT. This is interesting because the swap operation was symmetric. It didn't matter which went in which, the operation was the same. A controlled NOT is not like that. Order matters. So let's look at this. We have two inputs. One is called the target and one is called the control. So the control does not change. And if the control is white, then the target does not change. If the control is black, then the target changes. So we can see here that for the two left-handed operation, the control ball was white. And so the inputs and the outputs are the same. For the second operation, the right-hand column, we can see that the control ball was black. So that means the output applied a NOT. We applied a NOT to the target. And so the output of the target is opposite of the input. All right, so let's try a few. Okay, let's go through them. So first we swap the black and the white. So now the top ball is white and the bottom ball is black. And then we apply the C0. And the C0 control is white, which means the outcome will not change. Now let's look at the second one. We have the NOT gate, which toggles the black ball from black to white. And then we have the C0, and we can see this, the C0, in this case, the control is black. And so we will toggle the value of the target. So now the target becomes black. And now we have two black balls going into a swap. And we know that if we have two of the same value going into swap, then none of the values change. So we end up with two black balls. Okay, let's look at this one. I want you to look at this picture very carefully, because what's important here is that I've swapped the order of the control and target on the second one. Because the order of the inputs matters, we can connect the C0 in either way we want. And so you can see that the symbol, the filled in spot versus the plus sign with the spot, are opposite in these two. So we're going with a 0 and a 1 into the first C0 gate. And in the first C0 gate, the control is white. And so we end up with a white ball and a black ball in the first one. But in the second one, we can see that now the control is black. And so we will toggle the top bit. Okay, so I just want you to be aware that when you're looking at a C0, it is not always the case that the control is on top and the target is on the bottom. You always have to look for that symbol.